Good afternoon. Hi, so I'm going to give a brief kind of introductory lecture on some of the chemical constituents of seawater. And this is mainly meant to serve as a companion to the Ocean Data View lab that has been up all week. And so I'll be mainly focusing on some of the chemical components of seawater that you're plotting in that Ocean Data View lab. So why study marine chemistry? As many of you probably already know, 50% of the oxygen produced and available in our atmosphere to breathe on this planet comes from the ocean. The ocean is also responsible for taking up about 25% of the carbon dioxide that's produced by humans, helping to maintain our current climate and keep us from overheating quite so quickly. And the nutrients in the ocean also support all of the life from the bottom of the food chain on up, including fisheries with 70 to 100 million tons of fish that are caught worldwide each year, feeding a lot of the world. So there are a lot of different types of chemical constituents of seawater. Salt is perhaps the one you would think of immediately, as well as nutrients, macronutrients, things like nitrogen and phosphorus in particular, organic matter that is produced by the life living in the ocean, specifically the base of the food chain, the phytoplankton that fix carbon dioxide and produce organic matter. There are also gases that end up dissolved in seawater. Oxygen is, of course, important for life in the ocean, and other gases as well. Then the carbonate system, which there are a couple of great lectures up about the carbonate system where you can learn a lot of detail about that. Intro to ocean acidification and advanced topics in carbonate chemistry. So check those out on the website. And then trace metals, which can also play roles as nutrients as well as forming other types of complexes in the ocean. And Julia has a talk on that. So I like this periodic table of the elements, but in the ocean, where you can look at all of the elements and see that the distribution of these different elements is not the same. And this is because different physical and biological processes are acting on different elements in different ways to result in these different profiles. For example, if you look at something like oxygen, you can see it's pretty elevated in the surface, like you might expect that if the water is equilibrating with the atmosphere and oxygen is getting mixed into the surface water. And then you see that it goes down as oxygen is consumed by microorganisms breaking down organic matter in the water. In contrast, nitrogen, which is right next door to oxygen, shows a very different profile where it's extremely low in the surface and then becomes more elevated farther down in the water column. And this is because it's consumed by the primary producers, phytoplankton that are fixing carbon dioxide, and is then remineralized deeper in the water column. And so each of these elements has a slightly different story of the processes that are shaping their distributions in the water. And that is one of the goals of chemical oceanography, is to understand the controls and what's shaping these distributions and what that can tell us about how the ocean works. So before I dive in, I just wanted to illustrate how we go about collecting chemical samples in chemical oceanography. This is a picture of a research vessel getting towed out to sea in Montevideo, Uruguay, on a month-long research cruise that I was on a few years ago. And to collect samples, we send these rosettes over the side. They have what are called Niskin bottles that are capped at both ends, and then as it descends through the water column, we can send a signal and the caps will snap closed. So right now what we're looking at is the rosette being retrieved. So all the bottles are already closed because we've collected water samples. There's also a CTD, which stands for conductivity, temperature, and depth, that allows us to know the salinity and the temperature and the pressure, so we know what depth we're at as we're collecting those samples in real time. And then a lot of chemical oceanography depends on what you're measuring, but often involves a lot of filtering. Certainly my work, where I'm looking at organic molecules, to collect the samples, we have to filter a lot of water to have enough material to measure using mass spectrometry, and to extract dissolved molecules, we also need a lot of water to do solid phase extractions. So lots of water, lots of filtering once you get samples back on board the ship. So I wanted to start off with kind of the simplest chemical parameter that we all think of when we think of the ocean, that is salts. And they're important for both chemically and physically. They contribute to the density of seawater and thus how the ocean circulates. They change the freezing point of water, the ionic strength, which life in the ocean has to adapt to the ionic strength of the water that it lives in. It affects the reaction potential or activity of the molecules in the water, and can also create a lot of analytical challenges that I personally deal with in my work in terms of interfering with the molecules that I actually want to be measuring and corroding and destroying instruments. So if you take a liter of seawater and got rid of all the water, you're left with 35 grams of salt still. Of course, most of that is sodium and chloride, as we think of, but a number of other ions are pretty important to that overall salinity as well, including sulfate and magnesium, calcium and potassium being the major other contributors to those 35 grams of salt in a liter of seawater. And for all of these chemical constituents that we're thinking about in the ocean, it's helpful to think about, as we understand what's controlling their concentrations and availability in the sea, it's helpful to think about the sources and the sinks for these constituents. So important sources might be river water flowing into the ocean, or mixing with the atmosphere if it's a gas, or you could have inputs coming from hydrothermal circulation, or some sort of exchange with the sediments. And so all of these different processes can be contributing or removing different chemical constituents, and that shapes the concentrations and abundances of these chemical constituents in different regions of the ocean, as well as the overall reservoir of that chemical constituent in kind of the world ocean. And when we've determined all of these sources and sinks, or inputs and outputs, what's getting put in and removed, we can estimate the residence time, or how long a molecule resides in the ocean before it is removed. And you can do this by estimating the overall ocean inventory of that particular molecule that you're interested in, divided by either the input or the output rate. So for example, if you wanted to estimate the residence time of water in the ocean, you can calculate how many, you can calculate how much water there is in the ocean, and then the total volume, and then divide that by the river inflow rate. So how much water is getting added. So you're assuming that how much water is getting added is also getting, that same amount is getting removed, and then you can calculate a residence time for water of about 40,000 years. And to illustrate how that can be helpful, let's look at salt. So if you calculate the residence time of sodium, one of the main constituents of the salinity of seawater, we can estimate how many moles of salt there are in the ocean of sodium and divide that by all of the inputs of sodium, and we get a residence time for sodium of 80 million years. And similarly, if we do that for chloride, we get a residence time similarly on the order of 1 million years. So these salt ions reside in the ocean about 3 times longer than water. So they're really, really not reactive. They're not doing much. Once they're in the water, they're just hanging out there. And this is in contrast to a lot of molecules that are interacting perhaps with the organisms that live in the ocean that have much, much shorter residence times than things like sodium and chloride, where they're just hanging out for 1 million years. So these estimates of residence time give us a sense of the types of processes that are controlling the abundances and distribution of these molecules. So, as I said, sodium and chloride aren't doing too much in the ocean. They aren't reacting. So, one of the main processes that does determine their concentrations in the water is just evaporation and precipitation. So if we look at this plot that's just showing sea surface salinity along latitudes, we can see that right at the equator, where there is less evaporation and more precipitation, we get a dip in salinity, but that on either side of the equator, around 30 degrees north and south, you get a peak in salinity because evaporation is greater than precipitation in those regions of the world. And then we see the opposite trend again develop as you move towards higher latitudes. So this is one of the big determinants of sea surface salinities out in the open ocean, where you don't have inputs from, say, a river, where you could have a really reduced salinity in a certain region because of freshwater inputs. And so we can visualize this looking at the global sea surface salinity, and you see that same trend where you look along, we see about 37 practical salinity units here. Way up here in the Arctic, it's 32. So you can see that trend holding true throughout the world ocean. And as I mentioned at the beginning, salinity is important for determining the density of seawater. So you'll find deep in the ocean different salinities in different water masses. And looking here, you can see a kind of lighter, low salinity layer floating right here in purple above a denser, higher salinity layer right below. And of course, temperature also plays a role, but we're just visualizing salinity here. Okay, so the other aspect of marine chemistry I wanted to touch on today is macronutrients. So I'm going to talk a little bit about nitrogen and phosphorus, two elements that all life requires to exist. We need it, and all of the life in the ocean, starting with phytoplankton at the base of the food chain, need it too. So nitrogen has a fairly complex set of different molecules associated with it, and its cycling is pretty complicated and still a big area of research. So N2 gas that exists in the atmosphere is not biologically accessible. So N2 gas has to get fixed or reduced into a usable form. And this primarily happens by diazotrophs, which in the ocean are cyanobacteria generally. Organisms like Prochlorococcus, Synechococcus, Trichodesmium. These microorganisms can fix N2 and convert it into ammonium and thus organic nitrogen. And from there, organisms in the oxic ocean will go through a process called nitrification, where this organic nitrogen and ammonium gets converted through a series of steps and oxidized to nitrate, which is also an accessible form of nitrogen for living organisms. This nitrate, which is the most abundant form of nitrogen in the ocean, can be removed through a process called denitrification, which happens in anoxic regions of the ocean. And this occurs because certain specialized microorganisms can use nitrate and nitrite, which is the reduced form of nitrate, as electron acceptors. Just as in the oxic ocean, organisms are using oxygen as an electron acceptor. In an anoxic region, your second best option after oxygen is nitrate, or after that, nitrite. So it gets reduced through this process of denitrification back to N2. There's another process called anammox that is another way of denitrifying or removing, converting nitrite back to N2. And I'm not going to go into the biology and the enzymes responsible for this here, but just know that you can have all of these different forms of nitrogen, and it plays a role not only as a nutrient, but also as an electron acceptor for certain species. And so, as I mentioned, nitrate, shown here as the combination of, in the upper plot, as the combination of nitrate and nitrite, because nitrite is very low, and due to how these compounds are analyzed, it's easier to just report the combined concentration. Nitrate is the most abundant nitrogen species, and you can see that it's very reduced in the surface because it's a nutrient that's drawn down by primary producers, phytoplankton, that are photosynthesizing in the surface waters, and they draw it down, but then it's abundant at depth after it's gone through the process of remineralization, and organic nitrogen has been converted back to nitrate. In contrast, just to give you a sense of the difference in concentration, I'm showing nitrite along the same ocean transect, and you can see it is orders of magnitude less abundant than nitrate, and also see its peak concentrations show up in very specific locations closer to the surface, unlike nitrate. And I'll get into some of the processes that are producing nitrite in a little bit. So in the deep ocean, which we were looking at just there, you can also see differences in the nitrate concentrations between the Atlantic and Pacific that reflect the global ocean circulation that's occurring. So as surface waters sink in the North Atlantic, there's more nitrate in the water still, or there's less nitrate because surface water's nitrate has been drawn down by primary producers, so it sinks. There's also more oxygen in that North Atlantic water because it was just interacting with the atmosphere. And so it sinks, and then as it moves south through the Atlantic into the Indian Ocean and then into the Pacific Ocean and goes up the Pacific Ocean in these deep water masses, the process of remineralization continues. So the dissolved oxygen concentrations continue to go down while the nitrate concentrations continue to go up through this process of remineralization. And I just think it's really cool that you can see this difference that's reflecting ocean circulation between the Atlantic and the Pacific. So I mentioned I was going to talk about both nitrogen and phosphorus, and since these are two essential nutrients for phytoplankton, the base of the food chain in the ocean, and they can be limiting nutrients that keep phytoplankton from just growing and growing and growing. And it was for a long time thought that nitrogen primarily was the limiting of those two nutrients, was the one phytoplankton ran out of first. So that was the limiting nutrient. And that's kind of reflected here in this plot where if you just look at the inorganic species, so nitrate, nitrite versus phosphate, you run out of nitrogen. So you have zero nitrogen when you still have a little bit of phosphate left. But if you compare that to just total nitrogen and total phosphorus, so including organic species, you actually end up hitting on the y-axis where there is no more phosphorus left, but still a little bit of nitrogen left, suggesting perhaps depending on bioavailability and what these compounds are, that phosphorus can also be limiting for phytoplankton. And as an example of this, I'm showing this figure that illustrates all of the different kind of organic forms of phosphorus that you can have. So there's just inorganic phosphorus or phosphate that is easily used by organisms, but then phosphorus is also a part of DNA and RNA, so nucleic acids, and there are other forms of phosphonates and other types of phosphorus containing organic molecules that are still being studied. So these can all also provide small but valuable forms of phosphorus to organisms. And so I'm showing a similar plot here that I showed for nitrate and nitrite, but this is phosphate. Again, you can see that its concentrations vary in different deep ocean masses. but that it is also has that nutrient profile where it is very depleted in the surface waters. And I wanted to just contrast that with this plot that shows, so SRP stands for soluble reactive phosphorus. For our purposes, we'll just think of that as phosphate, so the inorganic phosphorus. And you can see, again, the depleted in the surface and increasing with depth. And then compare that to the dissolved organic phosphorus, which you see elevated at the surface, where it's produced by all of the microorganisms living in the surface waters, and then decreasing as processes like remineralization occur with depth. And so you can see in the surface waters that dissolved organic phosphorus is actually a pretty important component of what phosphorus is available. In this particular case, this is a site in the North Pacific near Hawaii that is continuously monitored for a variety of parameters. And actually, their data is publicly available if you want to look up Station Aloha and look at some time series data. So I wanted to talk about a region of the ocean briefly where nitrogen cycling gets really interesting. So this is off the coast of Namibia where the Benguela upwelling occurs. I'm not going to go into the physical oceanography. Some of the other lectures this week probably covered some of this, but suffice to say that combination of Coriolis force and wind results in upwelling off the coast of Namibia. And you can see that here in the colder water moving up from depth along the coast. And with that colder water, as I've been showing in all of these plots, phosphate and nitrate are much more abundant. So with that deep water also comes nutrients. And as they arrive in that really depleted region up on the surface, they stimulate phytoplankton blooms. For example, like this one shown here, where you can see really high phytoplankton abundances using those nutrients that normally aren't available to really take off and do a lot of photosynthesizing. So this process of carbon fixation where they're using carbon dioxide to create organic molecules that they need. And consuming and producing oxygen also as a side product. And this can be organisms like diatoms and coccolithophores, which I'm just showing here because they're beautiful. Diatoms are made of use silica as part of their shells that can be thought of. So they're kind of glass-like structures. And then coccolithophores use calcium carbonate to create these beautiful frustules. So with these large phytoplankton blooms, you get eventually, especially with those shells, these organisms will start dying and sinking out, and heterotrophic microbes that can utilize all of the organic matter that's been produced as a result of primary productivity photosynthesis start to gobble up all of that organic matter. And to do that, they have to use an electron acceptor. In this case, oxygen is the best if it's available. And as they sink out, so they start to draw down oxygen, you can also see an increase in carbon, inorganic carbon, as they sink out and remineralize oxidize organic matter back to CO2. So that process is drawing down oxygen because oxygen is required for that remineralization process of organic matter. And this creates low oxygen zones, which, as I mentioned earlier, is where denitrification can occur. And it is estimated that about 30 to 50% of fixed nitrogen that is lost from the ocean occurs in these oxygen minimum zones that are created in these upwelling regions. So I want to return to this plot that I showed earlier because there's something else that it can show us, which is the slope of these lines, which if I calculated would be about 16:1, which is about the ratio of nitrogen to phosphorus that we find in living material, in inorganic nutrients in the ocean, as well as the ratio that's taken up by living cells. So this is approximately how much nitrogen to phosphorus is needed for life. Which makes sense if you think about it, that nitrogen is required in all of our amino acids and proteins, which are playing a role in all of our enzymatic reactions in any living thing. And phosphorus is essential for DNA and RNA, which is a less abundant, although equally essential component of life. So this ratio can also help us tell when different types of processes might be occurring that are changing that ratio of nitrogen to phosphorus in the ocean, since typically that's the ratio we see. And I wanted to say that before I got to this plot that's also showing the Benguela upwelling region, where they can identify that nitrogen is getting removed through this denitrification process by looking at the difference between the nitrogen abundance and the phosphorus abundance, and that is this nitrogen deficit. So that's how much the nitrogen abundance is deviating from that 16:1 ratio. So you can see where it's negative, that indicates that you're losing nitrogen through this denitrification process. Also, as part of this denitrification process, because it takes multiple steps, when you look at an oxygen minimum zone, you will notice different chemistry than in other regions of the ocean, particularly this increase in nitrite as an intermediate in denitrification. So the first step would be to reduce nitrate, and then the next step would be to reduce nitrite. And so you get this hump in nitrite in this low oxygen zone. And you also get an increase in microbial abundance because the microbes that can use nitrate or nitrite as electron acceptors are more abundant in these zones, taking advantage of that combination of available electron acceptors and the low oxygen. And then I wanted to move to a very, very different scenario. So that's a naturally occurring process that we see in the ocean. But we're also kind of creating similar scenarios for ourselves in a process called eutrophication, where when we use fertilizers in our fields or sewage or runoff from factories, all of that is running into coastal waters where, again, it's nitrogen predominantly and phosphorus, can stimulate algal blooms, which are problematic both from the perspective that they can act just like I was talking about in oxygen minimum zones, where they the consumption of the organic matter produced by those algal blooms draws down oxygen to such an extent you create dead zones, but it can also stimulate harmful algal blooms, so not just your usual phytoplankton, but ones that can be harmful to humans, creating toxins that can cause shellfish poisoning or fish kills. And then, as I was saying, hypoxia, regardless, when you create so much organic matter that then gets consumed, oxygen gets consumed along with it. And as an example of this, close to where I used to live until very recently, the Chesapeake Bay had a huge problem with this, and they've been working for years now to help this bay recover. But you can see this was back in 2005 that there were still huge dead zones where oxygen had been drawn down to such an extent that really nothing could live there. And this was due to runoff, nitrogen runoff from all kinds of different industries, from agriculture, sewage, things from power plants, septic systems, and just, yeah, all of these things we produce as part of normal human activities. So it's really important to understand these, how these nutrients are cycled, both for natural processes like upwelling systems, as well as regions where we're having an impact on nutrient availability and thus upsetting the balance of the ecosystem. Yeah, and I'm gonna leave it there. There's obviously a lot more to talk about ocean chemistry, but I wanted to highlight those topics so that when you're working with the Ocean Data View data, you can be thinking about some of these processes when you're looking at them. So please feel free to reach out on Slack to ask me any questions about this.